So, in this class, we are going to discuss the nomenclature, the relation between electronic configuration and the periodic table. Now, from here onwards, the old periodic tables, all of them, we are going to just throw it away. Okay. From here onwards, we are only interested in the modern periodic table. Okay. So, nomenclature of elements with atomic number greater than 100. Because see, till 100 we know all the elements in the periodic table, every single element till the 100th point we know. Okay, so so basically we need a placeholder for names. So if a person discovers an element, pare, okay, if you say that let's say you discovered an element, masla cha, you element discovered padena, you still haven't named it, but what will the other scientists call it? What will the other scientists call it is basically the question, right? Now, wait a minute. So basically, so they all decided that we need a nomenclature placeholder to just call them. Okay, just call them and understand what their things are. Okay, so we are going to discuss about that. The IUPAC appointed a commission on nomenclature of inorganic chemistry in 1994 to give a rational system of nomenclature for elements having atomic number greater than 100 until their discovery is proved and they got an official name. Once the discovery becomes proved, the person who discovered the element has the right, as we all know, the person who discovered the right has the right to also name the element, right? Okay, so the basic rule to write the name of an element in accordance with the system of nomenclature are: the name of the element is derived directly from its atomic number using the numerical root for 0 and numbers 1 to 9. The roots are all tabulated below. So basically, for every single number we have a certain name. So nil, un, bi, tri, quad, pent, hex, hept, oct, n. Okay, n. Okay, so all of these are various types of names that we can use. Okay, only nil, un, and n. That's the only place I want you to stress yourself on, because those will be the numbers that will be used the most. To write a name of an element, the roots are put one after the other in the same fashion of digits as in the atomic number, and the suffix em is added at the end. For example, the element with the atomic number 108 is named as 108. 108, how does it go? 100, that is un, nil, oct, em. Un, nil, oct, em. Understood? So 108 will become what? Un, nil, oct, em. Clear? Un, nil, oct, em without any spacings. Okay. So Drupad, try for 112. What do you get for 112? Un by em. That is correct. Finished. Okay. So to write the symbols of elements, put the first letter of the root in the same order of digits as in the atomic number. The system for elements having atomic number 108 is UNO. The first element of the symbol must be put in upper space. Okay, so this is so Drupad, what do we need? We need both the name that you said right now, un by em, that is 112, un by em. So we also need a short form, right? For example, iron we called Fe, for copper we called Cu. So we also need a method to basically represent them in that formula form. Okay, so basically un by em will become UUB. Okay, what will this become? Let's say let's look at this. Let's look at the values. Okay, so 101 is un, nil, un, em. So UNU becomes the formula. The formula name for our element 101 becomes un, nil, un, em, and we now know that it is called Mendelevium. Similarly, for 107 we have un, nil, Hept or sept? Is it hept or sept? Sept. Un nil sept eum. So the formula will become U N S. UNS. Okay, so this is how you can figure out all the formulas. This is how you can figure out all the formulas, right? Is there a doubt? Okay, fine. So you don't need to remember these. Okay, nobody remembers these because people who are like 100%, they remember everything. Those are the people who remember the whole periodic table. You don't need to remember them, but this is how the question is going to come. Okay, so I'm just going to give you two questions. What is the what will be the number for 120 and the formula? What is the formula for 132? 132. Un try by em. Okay, so what will be the number? What will the formula? UTB. Okay, in the last one, you even when you are saying 130, you said un try em. No, un try nil em. That is how you phrase it. You need to use all three of them. Zero has a name. Un try nil em becomes 130. Okay, let's move on. All these elements man-made through artificial nuclear reactions. The new elements first get a temporary name with symbol consisting of three letters. Later, permanent name and symbols are given by vote of IUPAC representatives for each country. As of now, elements with atomic number up to 118 have been discovered. Official name of all elements have been announced by the IUPAC. What would be the IUPAC name and the symbol for the element with atomic number 120? Okay, and the formula? UBM. So un by nil em and UBM. Okay, next. Okay. So configuration and types of elements. So the whole periodic table is broadly differentiated into four parts. You have the S block elements, the P block elements, the D block elements, and the F block elements. The S block elements are the elements that are placed to the left of the periodic table. The P block elements are the ones that are placed to the right of the periodic table. The D block elements are placed in the middle between the S block elements and the P block elements, and the F block elements are placed below the periodic table. At the bottom of the periodic table, the two rows that you get, the lanthanides and the actinides, both of them are placed below the periodic table. So this is how the S, P, D, E, and F elements look. Okay, so basically there are two exceptions in this category. That is, where do we place hydrogen and where do we place helium? These are the two big questions that arose when people were designing the modern periodic table. What is the modern periodic table based on? Atomic number. Can you please tell me the definition too, like the whole statement? The chemical and physical properties of elements can be studied as a function of their atomic number. Okay, the periodic repetition of elements in the atomic number shows us similarities between various elements in the periodic table. Okay, so next, general characteristics of those blocks are described below. During this discussion, certain terms have been used, descriptions of which have been provided later in this chapter. The S block elements, the elements in which the last electron enters the s orbital. Okay, the elements in which the last electron enters the s orbital is called the S block elements. Since S subshell has only one orbital which can accommodate a maximum of two electrons, that is the reason why you only have two columns. Understood? The reason why you only have two columns is because of the fact that there are only two positions available in the s block elements. Okay, there are only two electrons that can be accommodated in an s orbital. Okay, similarly, how many electrons can be accommodated in the p orbital? 6. So beryllium, boron, sorry, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, understood? Then you have sodium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. All of these are p block elements. So because their p orbital can only accommodate 6 electrons, so each p block element will have how many columns? It will have 6 columns. The d block elements can accommodate how many electrons? The d orbital can accommodate how many electrons? 10. So that is the reason why there are 10 columns. There are 10 columns. Scandium, titanium, sorry, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are the 10 elements in the first row of the d block elements. And finally, how many electrons can be accommodated in the f orbital? 14. So there will be 14. Unfortunately, I don't know the 14 elements. Okay. So next. So the general electronic configuration. So basically, wait. Yeah. Since s subshells have only one orbital which can accommodate a maximum of 2 electrons, so only two groups, that is the group 1 which is called the alkali metals and group 2 which is known as the alkaline earth metals, okay, belong to this block. These groups lie on the extreme left of the periodic table. General characteristics of elements of this block are as follows. The general electronic configuration of elements of this block is NS1 to 2. Okay, so it can either have NS1 or NS2. For example, 2S1, 2S2, 3S1, 3S2, 4S1, 4S2. Like this, you can have, can you see a pattern? The pattern for the S block elements is NS1 to 2. Okay. Okay, thus the valence shell configuration of alkali metals is Ns1 and the alkaline and earth metals becomes Ns2. These are soft metals with low boiling and melting points. Because of their low ionization enthalpies, these metals are highly reactive. Now, what is an ionization enthalpy? You're going to learn this after your exam. But for now, an ionization enthalpy is the amount of energy that is required to remove the outermost electron. So basically, if you want to make sodium Na plus, you have to remove an electron. Yeah, so the energy required to remove that electron is known as the ionization enthalpy, and that is extremely low for the metals in the alkaline elements and the alkaline earth elements. Okay. Yeah, that is the reason why they are highly reactive. They are so reactive that sodium, if it comes in contact with where water, just boom, it just explodes. Okay, so because of their low ionization enthalpies, these metals are highly reactive and hence never found pure in nature. In the 10th class, do you remember we said that there are some elements that are found purely in nature? Those were the basically gold, silver, platinum. These were found raw in the nature, right? But then we had the elements which had low reactivity like iron and copper and all that stuff. But then we had some elements that were extremely reactive, that the only way to purify them was through how, which type of refining? Electrolytic refining. Exactly, you still remember. Okay, fine. Because of their low ionization enthalpy, these metals are highly reactive and hence never found pure in nature. Reactivity of these metals increases on moving down the group as the distance between the valence electron and the nucleus increases. Okay, so what is happening every time you're going down the group? In the structure of atom chapter, we have learned that every single time you go down the group, the number of shells increases, right? For example, hydrogen has only one shell, sodium has two shells, then you have potassium has three shells, then you will have lithium, sodium, potassium, rubidium. Potassium, rubidium will have four shells. So as you go down the group, the number of shells keeps on increasing. If the number of shells keeps on increasing, then what happens? The distance between the outermost electron and the nucleus also increases. Okay, and we all know that there is something called an effective nuclear charge, right? The effective nuclear charge, the charge which is holding all the electrons in position, right? And in the second chapter, we also discussed the shielding effect, the effect that basically repels the inner electrons, which repel the outer electrons, okay, and push them to go outward, is called the shielding effect. So both of them combined together, what do? They increase the size of the atom as you go down the group. So lithium will be the smallest alkali metal, whereas francium will be the largest alkali metal. Okay. So next, both they are electropositive and metallic elements. Their metallic character also increases on moving down the group. Okay, they are metallic characters, and what happens? Their metallic properties also increases down the group. They are strong reducing agents. They are strong reducing agents. What is the reducing agent, Drupad? Exactly, that oxidizes itself. They are reducing agents. So basically, they themselves get oxidized and reduce the person who is next to you. Okay, clear. Okay, they show plus one oxidation state in case of alkali metals, and they show plus two oxidation states in the state of alkaline earth metals. That is the reason why you see Na plus, L plus, Li plus. Then you have lithium, sorry, potassium plus, and similarly you have lithium beryllium 2 plus, or you have calcium 2 plus. Okay, this is the reason why, because see, one thing we know is that their outermost shell only has one electron. Okay, but the other thing is that they have a plus one oxidation state, and the other one has a plus two oxidation state. Okay, now they are predominantly ionic with the exception of those of lithium and beryllium. Okay, lithium and beryllium, because they are so small in size, their effective nuclear charge becomes really, really large. The electron that is present in the outermost shell of lithium and beryllium is so close to the nucleus that lithium refuses to give its electron. Okay, lithium refuses to give its electron. It generally prefers to share the electron with someone else. So lithium and beryllium usually form covalent bonds, covalent compounds. Okay, but the rest of them, sodium chloride, as we all know, it is an ionic compound, right? Sodium is a cation, whereas chlorine is an anion. Okay, next. Alkali metals like potassium, rubidium, cesium are used in photoelectric cells due to their low ionization enthalpy. Now, go back to photoelectric effect. What was happening there? A light of a certain frequency, when it fell on the surface of a metal, the electrons absorbed the energy, right? And then they basically did what? They came out of the metal. They came out of the metal, right? So because of these metals, they have very low ionization enthalpies. Even the normal visible light will have enough energy to ionize their electrons, to remove their electrons from the metal surface. Is it good? Done? Drupad, please tell me it's okay if it's okay or not. Okay. Hello, Drupad. Yeah, okay, fine. So the p block elements, the elements in which the last electron enters in any of the three p orbitals. Okay, what are the three p orbitals? The px, the py, and the pz, right? These are the 3p orbitals. Okay. Now, the elements in which the last electron enters in any of the 3p orbitals of their respective outermost shells are called the p orbitals of the are called the p block elements. Since a p subshell can accommodate a maximum of 6 electrons, thus 6 groups, that is from 13 to 18, are present in these p block elements. Elements of groups 15, 16, 17, and 18 are respectively called PNIs, nictogen, producers, chalcogen, and halogen and noble gases. Nictogen, P is a silent. Okay, nictogen, chalcogen, halogen, and noble gases. Okay, nictogen, nictogen. Okay, nictogen, chalcogen, carbon, halogen, that is, we know halogen compounds, fluorine, chlorine, bromine, iodine, and finally the noble gases. 15, 16, 17, 18. So the CAPE, they will ask you these things. Okay, they will ask you these things in the exam. Now, general characteristics of elements of this block are as follows. The outermost electronic configuration of these elements varies from Ns2np1 to Ns2np6. Ns2np1, it varies all the way to Ns2np6. Okay, in each period, that is, the general configuration for these elements can be written as Ns2np1 to 6. Okay, they are generally non-metallic, but some metals and metalloids are also present. The non-metallic character increases from left to right along a period, but metallic character increases on going down the group of this block. So, Drupat, you know what the difference between a metal and a non-metal is? Exactly. Metals can lose electrons easily and non-metals can gain electrons easily. So, what's happening as we go from left to right in a period? Okay, left to right in a group. No, I was right the first time. Where what happens when you go from left to right in a period? They are all present in the same shell. You can I both agree that along a period, all of the electrons that are going to enter will be in the same shell. So they will be effectively at the same distance away from the nucleus, approximately. I'm not going to go into detail about the S and the P. Still, most of them will have a, a similar position. Right? They will be at approximately the same distance from each other. Now, what is happening here? The latter elements cannot be protected by the shielding effect. This is also part of your syllabus only. We will do it. We will study it later, like half an hour later. But for now, you have to remember this. Okay. So as you move along the period, what happens? The effective nuclear charge also starts to increase. The effective nuclear charge increases, and there is no shielding. Okay, think about this. An army is becoming stronger and stronger, but the guards that you have in front of you is not increasing. So what happens? The distance slowly starts to decrease. When the distance slowly starts to decrease, the basically it becomes more and more difficult to remove the electron from the outermost shell because they are closer and closer to the nucleus. Okay, that is the reason why elements, as when you go from left to right, they start to become non-metal because it is not that they want to become non-metals, they are forced to become non-metals because their electrons are closer to the nucleus, so the nucleus is not willing to give out electrons. Okay, now another thing, if you go down the group, what happens? Every single new electron that you see is on a different shell. So now the effective nuclear charge is decreasing because of two reasons. You have an increased distance, you are at an increased distance from the nucleus, as well as you are also having a shielding effect. Okay, there is a shielding effect that is going on. Okay, there is a shielding effect that is going on. Okay, next. Yeah, so for p block elements, as you move from left to right, what happens? The non-metallic character starts to increase, but as you go from top to bottom, what happens? the metallic character starts to increase because of shielding effect and the increased radius and the decrease in effective nuclear charge. These three factors are responsible for making an element into a metal. Understood? Okay. Now they have high electron gain enthalpies and ionization energy. Both properties increases along a period from left to right and decreases on moving down the group. So electron gain enthalpy is what? What is an electron gain enthalpy? Exactly. Okay. What is the ionization enthalpy? The ionization enthalpy is basically if you want to ionize the element by removing an electron, it will become difficult for you because of the increased effective nuclear charge. The nucleus has now a stronger hold on the outermost electrons, and when you have a stronger hold on the outermost electrons, you have to supply even more energy. You have to supply even more energy to get the electron outside. Clear? Okay. Next. Okay, their oxidation character increases on moving from left to right along a period, and reducing character increases from top to bottom in a group. Okay, this is the exact opposite of what we discussed in the S block elements. So did you understand what the S block elements does? The oxidation character increases. See, basically the oxidation character is increasing. What is the meaning of oxidation character increasing? As you go from left to right, you will the oxidation will be faster. Okay, so basically, you're gonna learn in the future that if a non-metal joins an element, it oxidizes itself. If a non-metal is lost, it's a reducing process. Okay, similarly, when we discussed in 10th class, we discussed no. If you gain an oxygen atom, you are oxidized. If you lose an oxygen atom, you reduce. If you gain an electron, you reduce. If you lose an electron, you oxidize. So basically, the oxidation ability has now increased because of a third reason. If you give an electronegative element, if you attach an electronegative element, you are oxidizing. If you remove an electronegative element, you are reducing. This becomes a third property now. You have to remember that. Most of them are electronegative in nature. Okay, why are they electronegative in nature? Because they are hungry. They are hungry to satisfy their appetite and gain the extra electrons so that they can have a stable shell. They can have a stable shell around them. Okay, what do you need to get a stable shell? 8 electrons, exactly. You need to get 8 electrons. Now, group 1, 2, 13, 14, 15, 16, 17, 18 represents the main group of the periodic table. Hence, elements of these groups are collectively known as main group or representative elements. So, in the periodic table, the S and the P have the responsibility to represent themselves. Okay, so the S and the P have the responsibility to represent themselves. Okay, they are also known as the main group elements. Now, the D block elements are what? They are known as the transition elements, and like I discussed in the morning, the transition elements have the property to change as you go from left to right. Their property slowly and slowly stops being metallic and starts being more non-metallic in nature. So by the end, you start with non-metallic properties. Okay, elements in which the last electron enters one of the inner d orbitals are called the d block elements. Since these can be maximum of 10 electrons in the d shell subshell, there are 10 groups in the transition elements. There are 10 different groups in the transition elements. Okay, now the properties of elements of these groups are midway between the S block and P block elements. They act as a bridge between the highly reactive metals and and of the S block and the less reactive elements of group 13 and 14, that is, they show transition in their behavior, hence they are known as transition elements. They help us understand how the atom when it gains new protons and electrons, how the atom changes its behavior from going from a highly reactive species in the S block element to a mildly reactive species in the P block element. Okay, now this is how you see this transition. Okay, the more the number of more the number of protons and neutrons and electrons are added, they slowly and slowly shift their character as you move from left to right. Okay, so the general characteristics of elements of this block are as follows. General electronic configuration is what? You will say the D first, and then you will say the S. Okay, so basically 3D 4S. The general electronic configuration of elements is N minus 1D 1 to 10 and NS 0 to 2. Okay, N minus 1, 3D 4S, 4D 5S, 5D 6S, and 6D 7S. Okay, this is how it goes. So 3D 1 to 10, 4S 1 to 2. Okay, do you understand the logic how it's going? Okay, next. Most of they all are metals with very high melting and boiling points. Most of them form colored ions because of the presence of partially filled d orbital. You're going to learn more about this in the 12th chapter. You see, no, like there are various crystals of metals, like copper sulfate is what? Copper sulfate is the vitriol, blue vitriol in color, whereas your iron sulfate is what? Iron sulfate is green in color. All of these color properties that they have, we are going to learn more about this in the 12th class. Okay, they generally exhibit variable valency oxidation states because the 3D and 4S are of comparable energy levels and hence take part in bonding. Okay, they have variable valencies. They can have multiple valencies. Like for example, what is a valency, Drupad? What is the valency of calcium? Why do you say plus 2? What was the reason for you to say plus 2? Exactly, to become a noble gas configuration. But because there is such a correlation, there is such a similarity between the Sn minus 1 D and Ns or Ns subshells, that basically these electrons are like, shared property, shared community property. You can say that is the best way I can explain it to you. It's like a shared community property. It doesn't matter if the electron goes from 4s or it doesn't matter the electron goes from 3D. You just need to bond, right? That is the reason why they have variable valencies. The reason why they have variable valencies, another. So this chapter is completely based on theory. Okay, there is no numerical. The stronger the theory you know, the better you will be able to perform in tomorrow's exam. Okay, next. So they generally show paramagnetism because of the presence of. So what is paramagnetism? Paramagnetism is when you have unpaired electrons. Okay, when you have unpaired electrons in the orbitals, you say you are paramagnetic. Okay, you say that you are paramagnetic. Okay, if all the orbitals in the shell are completely filled, you call yourself dimagnetic. Okay, para means 1, di means 2. If all the electrons in your orbitals, every single orbital is full, then you say that you are dimagnetic in nature. But if you have unpaired electrons in any of the orbitals, then you are known as a paramagnet. Okay, paramagnetism. Because of the unpaired electrons in the d orbital, higher the number of unpaired electrons, more paramagnetic character it will show. Yeah. Oh, of course. The more paramagnetic you are, you have a higher chance of becoming magnetized. Dimagnetism basically they try to isolate themselves in a magnetic field. You will learn more about this in 12th class. If you place a dimagnet in a magnetic field, it's like they will behave as if the magnetic field around them is a plague and they will oppose them. They will not allow the magnetic fields to enter through their body. Understood? So paramagnetism and dimagnetism are different things. And then you have something known as the ferromagnetism, who are like basically it's like a drug for them. Okay, and all the electron, all the magnetic field just enters through them. So basically, they become really, really strong magnets. Ferromagnets are the magnets that are used in the case of this thing. You have seen cranes that lift cars and all of that stuff, right? So that's where you use them. So they are paramagnetic in nature. Why are they paramagnetic in nature? They are paramagnetic in nature because of the fact that they have unpaired electrons. Okay, next. So they are used as catalysts because of their variable valencies and partially filled d orbital. They can be used as a catalyst. What is a catalyst? An agent that helps in a reaction without physically, without actually getting consumed in the reaction. Okay, it participates in the reaction, but it does not get consumed in the reaction. That is, if you had this many number of catalysts in the beginning, you will have the same amount of catalysts in the end of the reaction. They do not get consumed in the process. Understood? They just help the reaction to either go fast or slow depending on what type of catalyst you use. Okay, next. The zinc, cadmium, and mercury. These are the exceptions of the rule at every single point. You know why? Now let's look at the electronic configuration of zinc, cadmium, and mercury. So, what is the electronic configuration of zinc, cadmium, and mercury, Dhruva? Zinc is 3d10 4s2, 4d10 5s2, and 5d10 6s2. The electronic configuration of zinc, cadmium, and mercury is 3d10 4s2, 4d10 5s2, 5d10 6s2. Okay, because of this, they have completely filled shells. And one of the main characteristics of d orbitals is that they have unpaired electrons. They are paramagnetic in nature. But because of this completely filled electronic configuration, their stable filled electronic configuration, they act as if they are the high class. They don't react like the others. They basically, it's like people who, who want to maintain their status and don't mingle with the society, right? Okay, they are these people. These are the like elites, you can say, who don't share any of the properties with any of the other elements in the D block. Clear? Okay. So zinc, cadmium, and mercury are an exception to almost any rule you throw at them. Any rule you throw at them, they will say, no, I won't follow like this. Okay, so zinc, cadmium, mercury, because of the presence of completely filled d orbitals, do not exhibit most of the properties of transition elements, and hence they are not considered as typical transition elements. Okay, so zinc, cadmium, and mercury are not considered as typical transition elements because of this property that they have, where they have completely filled d orbitals. Okay, typical transition elements have partially filled d orbitals in any of their oxidation states. Rest of all of them will have some one or two electrons will be missing. Some will have almost 9 electrons missing. Like basically the scandium. Scandium is what? 4 is to 3d1. It has only one electron in its outermost shell. Manganese is what? 4 is to 3d5. Okay. Next. The F or block elements, the inner transition elements, the elements in which the last electron enters an F orbital or of a anti-penultimate shell. Anti-penultimate shell is what? The penultimate shell is what, Drupad? The second last. The second last. The anti-penultimate shell is what? Third last. Okay, so like basically the last shell is S. For all these metals, the last shell is S. The penultimate shell is what? Second place. The anti-penultimate shell is what? It's just a fancy way of saying that he is third. Okay, so elements in which the last electron enters the f orbital of an anti-penultimate shell are called the f block elements. These are also called the inner transition elements because of the filling of the inner penultimate or the anti-penultimate shell by the last electron. These blocks contain two series of elements called the 4f and the 5f series, each of which contain 14 elements. The F elements of F series, that is from atomic number 58 to 71, are called the lanthanoids. You need to remember this. From where you start to where you go, you have 58 to 71. 50, just remember one and add 14. Okay, 58 to 71 are called the lanthanoids, and 90 to 103 are called the actinoids. Okay, are called the actinoids. These two series of elements are present at the bottom of the periodic table. General characteristic exhibited by the elements of this block are as follows. General outer electronic configuration for these elements is n minus 2, 4f 4 f1 to 4, 1 to 14, n minus 1 d, 0 to 1, and ns2. So Drupad, you know how it looks like? So you need to have 4f and 5f, right? It looks like this: 4f, 3, 4f, 5d, and 6s, or 5f, 6d, and 7s. These are the 4f, 5d, and 6s are the configuration for what? Lanthanoids. 5f, 6d, 7s are the configuration for what? Actinoids. Okay. So this is also done. So the general electronic configuration, you don't have to remember this. 4, 5, 6, 5, 6, 7. Finished. Okay. Next. Thus, the outermost electronic configuration, where blah, 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 come on, configuration for the lanthanoids and the actinoids are 4f1 to 14, 5d0 to 10, and 6s2. Okay, the s will always be filled. Okay, because you're going from the s, right? The s will be filled. You don't have to say s1 to 2. If you do, you're wrong. Okay, s2, and 5f1 to 14, 6s0 to 10, 5f1 to 14, 6d1, 0 to 1, and 7 2. Here also, Drupad, it is 0 to 1. You know why? I misspoke before. 1 to 10, 0 to 10 चुनेंगे, I was wrong. You know why? Because lanthanoids, no da, adalla. Look at the periodic table. It starts from here. Because it starts from here, there is P1. Okay, you have this. So 4f1 to 14, 3d0 to 1, because you can only have 0 to 1. Okay, 3d0 to 1, and you will have, and Drupad, 0 to 1, you don't have any question for 0 to 1. How 0? Yeah, okay, fine. So basically one of the electrons goes from the d to get there. Okay, fine. Okay, so 4f1 to 14, 5d 0 to 1, 6s2, and the other one will be 5f1 to 14, 6d 0 to 1, and 7s2. Okay. Okay. These are metals. Single one of them is a metal. Actinide exhibits a large number of oxidation states because of the comparable 5f, 6d, and 7s. Now, the shared community has increased a bit more. Okay, the shared property has increased a bit more. So, you have the 5f, 6d, and 7s orbitals, and hence their chemistry is more complicated as compared to the corresponding lanthanoids. However, the most common oxidation state exhibited by the F block elements is +3. Again, an MCQ question that is going to be asked tomorrow. What is the most common oxidation state exhibited by the actinoids? It is +3. All the actinoids are radioactive in nature. The first three elements, thorium, protium, protoactinium and uranium are natural, but the remaining from neptunium to copper are synthetic, man-made by nuclear reaction. We created these elements out of nowhere. Okay, so the thorium, protoactinium, and you have uranium. Okay, all these three are radioactive natural elements. They are radioactive natural elements, but rest of them from neptunium to coppercinium are all synthetic in nature. The latter are also called transuranic or transuranium elements, as they follow uranium in the periodic table. Okay, transuranic or transuranium elements. Trans okay, after the change. Okay, so transuranic or transuranium elements, as they follow uranium in the periodic table. Lanthanides are also known as rare earth elements because they occur scarcely in the earth's crust. You know where the rare earth element is the most abundant in the world? China. China has the highest amount of rare earth elements in the world. They are also known as, so lanthanides are known as rare earth elements. Okay, so the actinoids are what? Actinoids are all radioactive elements. The first three, what were they? The first three, thorium, protoactinium, and uranium. Okay, thorium, protoactinium, and uranium are all natural radioactive elements. Again, an MCQ can be asked from here. Okay, this is MCQ filled. Thorium, protoactinium, and uranium are natural, but from neptunium to coppercinium, all of them are radioactive man-made elements. Okay, so lanthanoids are known as rare earth elements. Because the presence of these elements in the earth is very small. Now, anomalies associated with the S, P, D, and F elements. Again, the position of helium and the position of hydrogen has always created a ruckus. Now, Drupad, the halogens, the helium, neon, argon, krypton, xenon, radon, right? Helium, neon, argon, krypton, xenon, radon, all of them are the last of the p block elements, right? Okay. Now, they are noble gases. They are noble gases. They are the last of the periodic elements. But except for helium, every single last electron enters the p orbital. That is the problem with helium. Okay, hydrogen and helium. So basically, according to the classification, shouldn't the question might be question that was risen was, then if the electron is entering the s orbital, shouldn't you place it in the s block? No, you can't place them in the S block because helium is a noble gas. It does not react with anybody. It's not its fault. It follows the principle of the completely filled orbital, right? It follows the principle that if you have a completely filled shell, then you are stable. It's not its fault that the first K shell can only accommodate 2 electrons, right? So basically, even though the electron in a helium atom, even though the last electron in the helium atom enters the s orbital, we still place it in the p or p block elements because of the commonality that it shares with all the other noble gases. Okay, the position of hydrogen has been a problem since Mendeleev. Right, even in Mendeleev's periodic table also we said that the noble gas here, the noble gas hydrogen will be a problem, right? Okay, so the electronic configuration of hydrogen is 1s1. Because of the presence of only one electron in s orbital, it can be placed in group 1 with alkali metals, but it can also accept an electron and to achieve the electronic configuration of the nearest inert gas. So it's like it can either gain an electron, it can either lose an electron. So basically, where do you place it then? Okay, is it a metal? Is it a non-metal? Okay, which is helium, like halogens, elements of the group 17. So it can also be placed along with them. Because of its unique behavior, hydrogen is placed at the top of the periodic table. Okay, like an odd duck, the black sheep. Okay, so because of its unique behavior, hydrogen is placed at the top of the periodic table. Next. Oh, sorry. Okay. Algorithm for predicting the position of an element. Okay. In In the prediction of position of an element in the periodic table, the following steps are involved. First, write the electronic configuration of the element. If not given, find the principal quantum number of the valence shell. It shows the period of the element. Predict the orbital which receives the last cyclone. It should be the block of the element. Okay, then you have the group of elements is then predicted as, if the element belongs to the S block, its group number plus number of valence electrons. Oh, what is it? If the element belongs to P block, group 10 is 10. Oh, it equal to. This is an equal to sign. What they are trying to say is, for example, sodium has one electron in its outermost shell, so its valency is 1, so its group is 1. Okay, if carbon has how many electrons in its outermost orbital? 14. Sorry, 4 electrons in its outermost orbital. You add 10 to it. Why are we adding 10? Huh? Because of the D block elements, we are adding 10 to it. Okay, nitrogen has 5 electrons in its outermost shell, right? So they are also known as 15, group 15, right? But what were the 15, 16, 17, and 18 groups called? Yes. Huh? Chalcogen, halogen, noble gases. Okay, fine. Okay. So if the electron belongs to the D block, group number is equal to number of electrons in the n minus 1 D subshell plus the number of electrons in the ns subshell. Okay. So 2 plus D block D orbital electrons will be the answer. If the element belongs to the F block, group number is equal to 3. If the element is in the F block, the group number is just 3. Okay. Next. Would How would you justify the presence of 18 elements in the fifth period of the periodic table? How would you justify how would you justify the presence of 18 elements in the fifth period of the periodic table? Hey, the bare. Say, you have the fifth period. Okay, fifth period has how many? It has the S block elements, the D block elements, and the P block elements, all of them. So you have 18 elements. That is how you justify there are 18 elements there. Understood? Because the fifth orbital is all of it, right? The sixth and the seventh. The sixth and the seventh is where you have the F block elements. Don't forget that. Okay. What is the configuration of F block? What? What? Fourth block also. Fourth. You mean fourth period, right? Fourth period also will also have 18 elements. Fourth and the fifth will have 18 elements. No, is there a doubt? No. And the sixth and the seventh. No, I didn't understand your doubt. Can you repeat that again? Okay, fine. Hmm. Okay, okay. Okay. General outer electronic configuration for these elements is n minus 2 f1 to 14, n minus 1 d0 to 1. We all did this, right? Yeah, position of hydrogen. I think we did this also. Okay. Now, idam not fun enough. We did this. Oh yeah, we were here. We were here. I'm so sorry. We were here. Okay. Now, the fifth. What is the answer that they have given? The fifth period belongs with the filling of the principal quantum number n is equal to 5. When n is equal to 5, L is equal to 0, 1, 2, and 3. But according to Aufbau principle, in the fifth period, electrons can be filled only in 5s, 4d, and 5p subshells whose energies increase in the order of 5s, 4d, and 5p. Thus, the available orbitals are 1 5s, 5 4d, and 3 5p orbitals, total 9 orbitals, which can accommodate a maximum of 18 electrons. Hence, this period contains 18 elements. Okay, so this is how you're supposed to answer it. Okay, my answer was incomplete. Okay, so basically, what did they say? The 5s, 4d, and 5p. The 5s, 4d, and 5p are the various orbit shells that you will have, the orbitals that you will have, and 5s can accommodate 2 electrons, 4d can accommodate 10 electrons, and 5p, 5s, 4d, and 5p, 5p can accommodate how many electrons? 6 electrons. Okay, so if they can accommodate 6 electrons, then 10 plus 6 plus 2 will give us 18 electrons. That is the entire analysis. Next, um, write down the outermost electronic configuration of alkali metals. How would you justify their placement in group 1 of the periodic table? So for lithium, it will be helium 2s1. For sodium, it will be neon 3s1. For potassium, it will be argon 4s1. For potassium, rubidium, it will be krypton, krypton 5s1. Okay, krypton 5s1, and then for the next will be xenon 6s1, and for the last one francium will be radon 7s1. Right, 7s1. The last one is 7. No, you have 7 periods. But you have 7 periods all in all. You can see you got frozen for a moment. Okay, no problem. So, hence, placement of all these elements of group 1 of the periodic table, because of similarity in electronic configuration and properties, thus it is also evident that the physical and chemical properties of these elements depends on their atomic number and not on their atomic mass. Okay, we knew this anyways. Okay, the element Z117 and 120 have not yet been discovered. In which family slash group would you place these elements, and also give the electronic configuration in each case? Electronic configuration of these elements are given as 117 will be what, Drupad? Which group will they belong to? Seventh group. And now which block? So இது எப்படி பண்ணுவா தெரியுமா? Hmm? You know how to do this? They basically, huh? Yeah, the second block, the B block elements. Okay, fine. Okay, so basically you need to know what the configuration, what the number of electrons for the halogen, for the noble gases are. Okay, if you know that, you can start from there, from radon 5f14, 6d10, 7s2, and 7p. And you also need to know the Aufbau chain. 1 is 2 is 2p, 3 is 3p, 4 is 3d, 4p, 5 is 4d. You need to know the whole thing. Okay, at least till 8 or 9, just remember them. Okay, till 8 you need to remember them. Okay, now the principal quant. So basically you will start with Redon. You will write 5f14, 6d10, 7s2 and 7p5. So 7s2 and 7p5 gives you what? It gives you, tells you that it's present in the 7th period, and the 5 tells you what? It is part of the halogen family. Exactly, the 5 tells you that it is part of the halogen family. Okay, for the next one is what? 120. So if 117 was what? 117 was halogen, 118 will be a noble gas. Yeah. 119 will be a alkaline metal. 120 will be a alkaline earth metal. So it is an alkaline earth metal. That's how you get it. You don't have to solve the whole thing. Okay. 120. There is no element like 120. We only have 180. No. So it will be un by nil em. UBN. UBN. Okay, fine. Did you understand this, right? Yeah. Okay, next. Write the name and the atomic number of the following elements. The third alkali metal. Yes, potassium. The fourth alkaline earth metal. You need to remember them by the groups. Okay, then the code is alkaline earth metal beta, beta, mange, car, santro, strontium. Strontium. Beta, mange, car, santro, bap, razi. Okay. So strontium is the fourth alkaline earth metal. The sixth element of the second transition series. Oh, who knows? Okay, I don't think they will ask you questions like this. Nobody is like expected to remember all of this. Okay, the fifth noble gas. Oh, we can do that. Fifth noble gas is easy, right? Helium, neon, argon, krypton, xenon, radon. Xenon. Xenon is the fifth noble gas. Okay. Now the second inner transition element. The second inner transition element. Inner transition element is what? F block elements. I don't remember them. Uh, Praseodymium. Praseodymium. They won't ask you questions like this. Otherwise, they have to give you the periodic table. Like they have to literally show you the periodic table. Like it could be a case-based question. It could be a case-based question where they give you the names of the periodic table and the atomic number, and they will ask you to tell which group do they belong to. Okay, so you need to know the intricate details of all of it. Like you need to know the first ones are called the alkaline metals, alkaline earth metals, and all the other names you need to remember. I think case-based could come from this question. They will just give you the periodic table and they will ask you 5 questions. Okay. Write the electronic configuration of the elements given below. Atomic number 11. That's easy, right? 1s2, 2s2, 2p6. That is 10. Then 3s1. 3s1. Right? Atomic number 27. That's also pretty easy. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2. I have reached 30. 1s2, 2s2, no, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2 I have reached 20. Then 3d7, 3d7. Let me just check. Yeah, 4s2, 3d7. That is correct. Then, so basically, Drupad, see, 1s2, 2s2, 2p6, 10 finished. 3s2, 3p6, 4s2, another 10 finished. Okay. Mantracha, Next. 54. 1:2, 2:2, 2p6, 3:2, 3p6, 4, 3d10, 4:2, 4p6, 4d10, 5:2, 5p6. So basically, this is it's a huge number. 1:2, 2:2, 2p6, 3:2, 3p6, 3d10, 3:2, 3p6, 4:2, 3d10, 4p6, 4:2, 3d10, 4p6. Then you will have 4d10, 5:2, 5p. Okay, fine. You can write it like this: 1:2, 2:2, 2p6, 3:2, 3p6, 3d10, 4:2, 4p6, 4d10, 5:2, 5p6, 6:2, 5d1, 4f1. Okay, so just practice these electronic configurations. Okay, just practice these electronic configuration. I still basically fail when it comes to f block elements. Okay, I make careless mistakes. Okay, yeah, that is my problem. So try to be better. Okay, just practice how to write the electronic configuration as fast as possible. Like I taught you how to basically look at the iota in complex numbers, right? So that your calculation becomes faster. So you need to do that. You need to practice that. Okay, I think we can leave these. Okay, next, metals, non-metals, and metalloids. Okay, so in addition to SPDF classification, elements can also be classified as metals, non-metals, and metalloids. Metals. These comprise more than 78% of all known metals and appear on the left side of the periodic table. They all appear where? They appear at the left side of the periodic table. Some important properties of metals are as follows. They are generally solid at room temperature with the exception of mercury. They are solid at room temperature with the exception of mercury, which is a liquid. Okay, they have high melting and boiling point except gallium and cesium, melting point of which is relatively 303 and 302. They will melt in your hand if you have a fever. If you have a slight fever, they will melt in your hand. Okay, now they are good conductors of heat and electricity, that is true, but except for mercury. Then again, zinc, cadmium, and mercury, they have completely filled d orbitals. We have learnt about this. No, we have learnt about this in the last 10th class also, that mercury is not really a good conductor of electricity, right? Okay, and what else? What else? They are malleable. They are ductile. What does malleable mean? Flattened, and ductility means they can be pulled down in strings. Okay, fine. They have high densities. All of these are most of them we know. Okay, it's not something that we have learned new. Next, nonmetals. They are present only in p block and occupy the top right side of the periodic table, although p block also has some metals and metalloids. So where are the nonmetals? They are only present in the p block elements. But are all the p block elements non-metals? No, all the p block elements are not non-metals. They are basically located in the top right corner, top right corner of the periodic table. Now, some important properties exhibited by non-metals are what they are. They can be solid, liquid, or a gas. Okay, example of a solid: carbon, diamond. Example of a liquid: your bromine. Bromine is a liquid. Example of a gas: all the gases: nitrogen, oxygen, carbon, all of it. Okay, now their melting and boiling point are very low, with the exception of boron and carbon. They are bad conductors of heat and electricity except for diamond and graphite. Except for diamond and graphite, they are generally brittle and neither malleable nor ductile. Okay, brittle. If you basically hit them, they will shatter. Okay, they will shatter, and they are neither malleable nor ductile. Okay, next, metalloids. These are very few in number and present in between the metals and the non-metals. We have learnt in 10th class that metalloids have both the properties of a metal as well as a non-metal. Okay, they exhibit the properties of both metals and non-metals. That's why they are called semi-metals or metalloids. For example, silicon, germanium, arsenic, antimony, tellurium, etc. In the periodic table, these elements form the zigzag line and separate metals from non-metals. They separate metals from non-metals. Okay, it's like a boundary. It's like a boundary fence between the metals and the non-metals. Okay, they're like the transition. It's like a transition from a metal to a non-metal. You need these metalloids in between. Okay, and here look at this, Drupad. Silicon and germanium. Without these two, the whole of the semiconductor industry would fall apart. Silicon, germanium, arsenic, antimony, all of these are used in the production of semiconductors because they share both the properties of a metal as well as a non-metal. They can be acted as switches. Okay, so they are like programmable gates. I'll teach you more about this in 12th class when we do semiconductors. There's a whole chapter related to semiconductors and how they can be acted upon as switches and all of the other stuff. Okay, they're basically programmable gates which allow the flow of current to be changed as the electricity flows through it. Okay, so these are the metalloids. Consider the atomic number and the position in the periodic table. Arrange the following elements in the increasing order of metallic characters: silicon, beryllium, magnesium, sodium, and phosphorus. Drupad, increasing order. Who is the most metallic? Who is the most metallic? Sodium. Sodium is the most metallic. No, that because see, look at this. It has so many cards playing towards it, right? It's in the left side. It is basically it has only one electron in its outermost shell. It will give away electron as if it's running for its life. Basically, it will just throw it away. Now, sodium, magnesium, beryllium, then you will have silicon and phosphorus. Phosphorus will have the lowest metallic properties. It's a non-metal, da. Okay. Okay, next. Okay, so these are the questions that you have to look upon. Okay, now try you can do them in your head. Okay, these are the questions that you have to look upon in your test. Okay, most of the Drupad, I would suggest you do all only those questions for the moment which have an NCERT next to it. Okay, because in chemistry always and always people have always asked questions from the NCERT. It's like even the board exam, most of the questions are directly lifted on from the NCERT. So please do the questions from the NCERT. Okay, now we are in the final, like basically this is the last topic that for your exam. This is the second last topic of the book, but the last topic for your exam. Okay, sorry, I'm sorry about that. So, periodic properties, atomic radii, ionic radii, and the ionization enthalpy. Okay, so periodic trends and properties of elements. There are many observable patterns in the physical and chemical properties of elements. Okay, so as we descend in a group or move across a period in the periodic table, here we will discuss the periodic trends in physical properties like atomic, ionic, atomic radii, ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity, as well as in chemical properties like valency, nature of oxides one by one. Okay, so this section, no, the chemical properties is a totally different section. That is the last and the final part of your chapter. Okay, for us, the beginning is the atomic radii. The atomic radii is defined as the distance from the center of the nucleus to the outermost shell containing the electron. Okay, the outermost shell, that is the atomic radius. Okay, now the outermost shell could be the K shell, L shell, M shell, and N shell. And as we all know, as you increase shells, what ends up happening? The distance of the radius also starts to increase. The distance of the radius also starts to increase. Am I right? Okay, fine. So, covalent, wait. So the determination of exact radius of an atom is not possible. It is not possible to determine up to like the most accurate level. But you can have like an error. It is permissible to have a slight error in your calculation. It is not possible because of the very small size, 1.2 angstrom of the atom, and since the electron cloud surrounding the atom has a non-shaped boundary, it's a cloud. It's a cloud. So, Drupad, like if I ask you, tell me the radius of Jupiter, you won't be able to do that with like zero point 0.1 millimeter accuracy. It's a cloud. The whole planet is a cloud, right? Yeah. Now, since the electron cloud surrounding the atom has a non-sharp boundary, thus atomic radii is generally estimated by the knowing the distance between the atom in the combined form. Depending upon the nature of combination atoms, atomic radii can be as follows. You can either have a covalent radii where basically both the atoms are sharing electrons in the middle, and you can have an ionic radii where you are not held together by a, like from by hand to hand. You are becoming a positive and a negative, and there exists an electrostatic force of attraction between the two, which is holding you together. Okay, clear? Okay, next. Now, covalent radius. If the combining atoms are non-metallic except noble gases, their radius is called covalent radii. The covalent radii is defined as the one half of the distance between the center of the nuclei of the two covalently bond atoms of the same element in a molecule. So basically, Drupad, if you have an O2 molecule, if you have an O2 molecule, you can basically figure out what the radius is going to be. How? You basically find the distance between the two centers of the nuclei. You find the distance between the two centers of the nuclei and you halve it. Sorry, you basically divide it by 2. You halve it. Okay, so the covalent radius is defined as one half of the distance between the center of the nuclei of the two covalently bond atoms of the same elements in the molecule. Now, that is, R covalent is half of the internuclear distance between the two covalently bond atoms with a single bond. For homonuclear diatomic molecules, homonuclear means what? Homo means what, Drupad? Same, exactly. So, homonuclear diatomic molecules are A is equal to D of A to A by 2. For heteronuclear diatomic molecules, then D of A to B becomes RA plus RB. It's obvious, right? The radius of A, the radius of the atom A plus the radius of the atom B will be equal to the radius, will be equal to the radius of the whole element. Now, yeah, tell me. Yeah, covalent bonds share covalent bonds. Yeah, tell me. Yeah, it's like imagine that there are two spheres not touching each other, but they are fused to each other. They're going inside like this, like an apple. Okay, it's similar to this. Covalent bonds don't actually look like this. Okay, Hey, it's fine. It's like basically the electron, it's I told you know it's an electron cloud. The electron clouds overlap. Okay, the two we are going to learn more about this in the next chapter. The next chapter is the chemical bonding. Okay, the next chapter for chemical bonding we are going to learn more about it. Okay, so how these two clouds overlap, how the orbitals overlap. We are going to discuss everything: head-on collision, sideways collision, all of that stuff. Okay, so where were we? Yeah. So RA to B is Ra plus Rb, where Da and Db are the distances between the two molecules. Okay, Da and Db are the distances between the two molecules. It should have been Ra and Rb. Okay, next, the metallic radii. In case of metals, the atomic radii is called the metallic radius, and it is defined as one half of the internuclear distance separating the metal cores in the metallic crystal. It could be like this. Okay, the metals just keep touching each other, and so this is the nucleus. Okay, so what is it? So the one half of the internuclear distance, one half of the internuclear distance by separating the metal cores in a metallic crystal. So this distance becomes the metallic radii. Understood? Okay, now in metallic lattice, the electrons are mobile and hence only weakly attached by the kernels. But in a covalent molecule, the electrons are strongly attracted by the nuclei of the combined atoms. Okay? So in a metallic lattice, the electrons are mobile and hence only weakly attracted by the kernels. Kernels சொன்னது தெரியுமா? Kernels means the balls, okay, the atoms. Okay, they are not strongly attracted like in the case of covalent bonds. But in a covalent molecules, the electrons are strongly attached by the nuclei of the combining atoms. Okay, now the van der Waals radius, inert gas radius. In case of noble gases, the atomic radius is called the van der Waals radius, which is defined as one half of the distance between the nuclei of two identical non-bonding isolated atoms. Okay, so they don't even have to touch each other. Okay, that is known as the van der Waals radius. But again, I'll repeat it. In case of noble gases, the atomic radius is called the van der Waals radius, which is defined as one half of the distance between the nuclei of two identical non-bonded isolated atoms. You then they cannot bond, right? Helium cannot bond with anything else. Neon cannot bond with anything else. So the interspacing, it is known as the nuclear distance, so the half. Okay, so next, since the van der Waals forces are weak and hence the internuclear distances between the atoms are held by van der Waals forces, it's much larger as compared to that between covalently bonded atoms. Just give me 1 second. Okay, just 1 second. Hello, can you hear me? Yeah, I just changed the mic. Okay, I just wanted to change the mic because the mic was dying. Okay, so I changed the mic and let's go back to the class. Okay, since the van der Waals forces are weak and internuclear distances between the atom is held by van der Waals forces, it's much larger as compared to the distance between the covalently bonded atoms. So what is this? Can you explain to me this line? Yeah, therefore large, exactly, it's large. Yeah, it is the distance between the two nuclei in a van der Waals bond is much larger than compared to a covalent bond. Here, van der Waals radius is much larger than the covalent bond. In other words, we can say that the radius of a noble gas is largest in its spirit. Okay, they have the largest radii, they have the largest atomic radii in their period. Okay, okay, next. So the order of different atomic radii is the van der Waals radius is the biggest, then you have the metallic radius, and then you have the covalent radius. The covalent radius is the smallest radii in the period. Okay, the van der Waals radius is also called the non-bonded radius, and it's radius of non-bonded atoms or molecules. Okay, so even so, this is what I was saying. This is what I was saying. See the covalent radius. Can you see it? These two atoms are merging with each other. Okay, they are like inside each other. So that is the covalent bond. The covalent bond is shorter. The covalent bond is shorter. You know why they are shorter? Because a physical overlap has to take place. A physical overlap between the two atoms clouds. The two orbitals have to occur for them to actually bond together. So that is the reason why they have the shortest. They have the shortest radii of all. The van der Waals is the biggest, then you have the metallic, and then you have the covalent. Okay? Screening effect and effective nuclear charge. I've already told you this. Okay, we all know. What is the screening effect? The repulsion that is faced by the outer electrons due to the presence of inner electrons, okay, is called the screening effect or the shielding effect. And what is the effective nuclear charge? The effective nuclear charge is the force with which the nucleus is holding all the electrons together. Okay, the effective nuclear charge is defined as the net nuclear attraction towards the valence shell electrons, or in other words, the actual nuclear charge whose static force of attraction is being experienced by the outer electrons. Okay, so the greater the effective nuclear charge, more tightly are the valence electrons bonded to it. More tightly are the valence electrons bonded to it. Understood? So, greater the effective nuclear charge, greater the effective nuclear charge, greater is the yes, exactly. So, lesser will be the radius. The radius will be lesser. Yeah. Okay. For the sake of convenience, we will use the term atomic radius for covalent, metallic, and van der Waals radii in this book. X-rays and other spectroscopic methods are used to measure the atomic radii. Understood? Okay. Now, what are atomic radii is? The metallic radii, the covalent radii, and the van der Waals radii, all of them together constitute the atomic radii. Variation of atomic radii in the periodic table. The variation of atomic radii along a period and in a group in the period are as follows. Along a period, variation along the period. Now, I have already explained this to you. Along the period, what happens? All the new electrons that are getting entered in the outermost shell. You have a doubt? Yeah. Okay, all the new electrons that are getting entered in the outermost shell, as we go from left to right, as we go from the alkali metals all the way to the noble gases, what happens is that they are present in the same shell. So all of them will be experiencing the same shielding effect, but the ones in the alkali metals will have a lesser effective nuclear charge compared to those that are present in the halogens, the pnictogens, the chalcogens. Right. So basically, what happens is as the effective nuclear charge increases, the nucleus is basically pulling the electrons towards itself and it is reducing the atomic radii. Okay, it is pulling the electrons towards itself and it is reducing the atomic radii. The radius generally decreases from left to right along a period as illustrated in the below graph for the elements of the second period. This is because within a period the outer electrons is added to the same valence shell, due to which the effective nuclear charge increases and hence the outer electron is held more tightly and therefore the overall radius decreases. Okay, so if the increase in effective nuclear charge and the lack of shielding, okay, there is no increased shielding along a period, that is why the atomic radii increases. Okay, now when you go down the group, Here it is important to note that the electrons in the same shell do not screen each other. You have to understand this. In the same shell, one electron cannot shield the other electron. Okay, for example, how many electrons are present in the L shell? 8 electrons. These 8 electrons cannot shield each other. Only the K shell electrons can shield the L shell electrons. Only the K and the L can shield the M shell electrons. The inner can shield the outer. But in a single period, all the electrons that are getting added are in the same shell. They're all in the same shell, so it does not work. Understood? Okay. So the nuclear charge is not compensated by the screening effect, and thus the radii decreases. What is the exception? The transition elements show a little variation in the atomic radii due to the poor shielding effect of D. So D orbitals do not shield properly, due to which what happens? There is no change in the radii across the D block elements. Or you can, to be more precise, you can say there is very little visible change in the radii as we go across period in the D block elements. And what is the reason behind it? The reason behind it is the D orbitals. See, the D orbitals are vastly outwards. Okay, even though we say that the d orbitals are inside, but they are spread across the atom like this. They are spread across the atom like this. So even though their job is to shield, they are not able to shield properly because most of their electrons are spread across. Okay. Next. The lanthanides also exhibit little variation in their atomic radii due to the lanthanoid contraction. We are going to learn more about this later, but for now, just remember this. Some phenomenon called the lanthanide contraction takes place, which reduces the size. Okay, now variation in a group. The atomic radii generally increases on moving down a group as illustrated in the following graph for the alkali metals and halogens. Okay, down the group the radii increases. Why? New shell, more shielding, right? New shell, more shielding, lesser effective nuclear charge, right? Okay, so that is the reason why the shell size keeps on increasing as we move down the group. Okay, now this is because of the electrons are added in a successive shell, the principal quantum number increases, and thus the electron of the inner shell shield the electrons of the principal energy levels from the pull of the nucleus. Due to the principal energy level from the pull of the nucleus, due to which the distance between the valence electrons and the nucleus increases, and hence the atomic radius increases. Here, note that the shielding effect is more pronounced than the effect of increased nuclear charge. The shielding effect is more pronounced because they are inside. They are inside. So basically, they can shield more properly the outermost electrons. Now, the variation of atomic radii with atomic numbers for alkali metals. Look at this, Rupert. Lithium, sodium, potassium, rubidium, and cesium. The orbitals are the size is increasing. Look at the jump from lithium to sodium and sodium to potassium. Why don't we see a similar jump in potassium to rubidium and rubidium to cesium? We see a huge jump in lithium to sodium and sodium to potassium, but why not for potassium to rubidium and rubidium to cesium? Why is there such a laughably small jump? Because of the poor shielding effect of the 3D and the 4F. Because of the poor shielding of the d orbitals and the f orbitals, they cannot shield properly. They had one job and then they failed at that job. Okay, now the atomic radii of noble gases are not considered here. Being monoatomic, their non-bonding radii values are very large. In fact, the radii of noble gases should not be compared with the covalent radii, but with the van der Waals radii of other elements. Okay, so we cannot compare the radii that we find from the van der Waals radius for the noble gases. We should use the van der Waals radius for other elements and compare it with them. Okay, even normal atoms can have van der Waals radii between the atoms of two consecutive intermolecular. We will learn more about this later. Okay, so I'm not going to say much on that topic right now. Okay. Finally, exception. Among D block elements, the radii increases from member of the first series to the corresponding member of the second, but the radii of the member of the second and third series are almost equal to to that of lanthanoid contractions. Due to lanthanoid contractions, they are pretty much similar. Okay, next. Ionic radii. In case of ions, the radii is called the ionic radii and it is defined as effective distance from the centers of the nuclei of an ion to which an influence up to which it has an influence in the ionic bond. Okay, it's like a trap. Okay, it's like a trap. The further the what is the closest distance you have to be to a sodium ion to feel its effects? That is what we call as the ionic radii. Okay, so how close can you go to a sodium atom without actually getting influenced by the electrostatic force that it is constantly projecting because of its positive charge is called the ionic radii. The distance between the nuclei of cations and anions, that is the internuclear distance in an ionic crystal, can be measured by X-ray method. By knowing the internuclear distance, the radii of one ion can be determined. Similarly, the radii of the other ion can also be calculated. The internuclear distance is what? It is the radius of the cation plus the radius of the anion. Okay, so it is equal to the radius of the cation plus the radius of the anion. Understood? Okay, now internuclear distance. Comparison of the ionic radii with corresponding atomic radii. The study of ionic radii leads to the following two generalizations. The size of the cation is smaller than its parent atom, right? We all know the size is smaller because, see, basically when once it loses two electrons, it loses the shell also, right? It's like when you retire, you don't hold on to your seat, right? When you retire, you leave your job. That is finished. Okay. Similarly, once the atom loses the two electrons or the one electron that is present in the outermost shell, that's it. It loses the shell entirely. Okay. Therefore, it is smaller than its parent atom. Okay. Now, in the same sense as the parent atom, consequently, the nucleus binds the electrons more tightly. See, Drupad, what is the effective nuclear charge? The force with which the nucleus is holding on to the electrons in the outermost shell, right? How much is every single electron experiencing the force? How much force is being experienced by each and every single electron in the outermost shell is the effective nuclear charge, right? It is the effective nuclear charge. Now, think about this. Okay, if the shell goes, if the outer shell goes, okay, then what happens? The next inner shell becomes the valence shell. Now the outermost shell, this inner shell becomes the outermost shell. Now, due to which what happens? There is more, the nucleus, the atom, will it shrink or expand? It will shrink because of the increased effective nuclear charge, right? Understood? Like basically, like if you are uh, I was going to give you an example, and I don't know. Yeah, like basically, like if parents go to work, they don't observe the children for a long time, right? But during the holidays, they have like the complete laser focus on the children. Like I was going to say that, but that's fine. Okay, next. What was the question? I'm so sorry to. What was the question, Dhruvat? Yeah, yeah. I have already told you the answer. No, it will shrink. You also told me it will shrink. Is there a follow up question to that? Okay, fine. Now, initially sodium had three shells. After it lost an electron, it has now two shells. The radii was 186 picometers. Now it's only 95 picometers. Imagine how small it must feel, right? Okay. The size of an anion is larger than its parent atom. Again, swababikam, right? Basically, you have an electron enter your system. You have an electron to enter your system, and then the effective nuclear charge is decreasing. Okay, if you can only hold like 10 objects in your hand, and someone comes and places another object, your whole balance shifts, right? The effective nuclear charge drops. The effective nuclear charge drops. So basically, anions are the result of addition of one or more electrons in an isolated gaseous system. Due to addition of electrons, the number of electrons increases, but the nuclear charge remains the same. Thus, more electrons are held by the same nuclear charge. That is, the effective nuclear charge decreases. Further addition of electrons also leads to the repulsion among electrons. Now, if you are adding an electron in an existing shell, okay, if you are adding an electron in an existing shell, then what happens? The existing electrons will start to repel each other, right? They will start to repel each other and try to go as far away as possible. And only way to go as far away as possible is going away from the nucleus itself. So the radii, the anionic radii becomes larger. The decrease in effective nuclear charge and the increased repulsion between the electrons in the already present shell, the increase in the so if you can just close your eyes, you can see this. Okay, you had 7 electrons. Okay, and now chlorine, when it gains an electron, it has to increase its atomic orbital, sorry, it has to increase its shell size just to accommodate for the 8th electron. Okay, right? It was like this, and now it's like this. Okay, this effect decreases the effective nuclear charge and increases the repulsion, result in less which results in lesser force of attraction and more distance between the nucleus and the outermost electron, which in turn results in an increased ionic radii. That's why the radius of an anion is always greater than its parent atom. Okay, an assertion reasoning based question is what I'm expecting from that particular sentence. Okay, now, is variance of ionic radii part of a syllabus? Variation of ionic radii is not part of a syllabus. But this is also an ionic radii only, no? Variation of ionic radii. It will only take. Let's do one thing. Let's just do this stuff. Ionization. Okay, fine. Yeah. So basically, we have somehow done it. Okay. We have completed your ridiculous syllabus. It is. I'm so scared what we are going to do in physics. Like I'm already terrified. Like how are we going to finish 2 chapters in 4 days? I don't know. I really don't know. Variation of ionic radii. What? Oh yeah, you have English too. You have English too. Oh my! So you will not be able to go attend one of the days, right? You are just increasing my BP. You're slowly killing me, Drupad. You're slowly killing me. Variation of ionic radii. Ionic radii shows same trends in the periodic table as shown by the atomic radii. That is, it decreases across a period and increases on moving down the group. Okay, so basically, we know this thing, right? It decreases across the period and increases down the group, right? So ionic radii shows the same trend in the periodic table as shown by the atomic radii. It decreases across the period because of the increased effective nuclear charge, and it increases down the group. It increases down the group. So isoelectronic species. What are isoelectrons? We learned about isotopes, isobars, isotones, and isoelectrons. What are isoelectrons? The same number of electrons. Exactly. Species, atoms or ions having the same number of electrons are called isoelectronic species. For the species, the number of atoms, number of valence electrons, and atomic structure all are same, but nuclear charge is different. Just because you flaunt having the same number of electrons as others, your effective nuclear charge will basically be the main determining point for isoelectronic species radius. Okay, if you have more number of electrons, if you have more number of electrons, but and your effective nuclear charge is very less, then your radius will be big. Okay, now let's actually look at this. Now, oxygen, fluorine, sodium, and magnesium. In case of isoelectronic species, as the magnitude of nuclear charge increases, force of attraction by the nucleus on the electrons increases, and hence the ionic radii decreases. Do you understand what I said? In case of isoelectronic species, as the magnitude of effective nuclear charge increases. So, can you please tell me how is the magnitude of effective nuclear charge increasing? Let's take the example of N3 minus, O2 minus, and F minus. All of them are isoelectronic because all of them have the same number of electrons, 8 electrons in the outermost shell. How will the ionic radii differ? Yeah, something like that. Yeah, because see, what I was expecting was you would say that the effective nuclear charge of the F minus is the most. Therefore, even though there are the same number of electrons in all the in the shells of each of these electrons, because of the effective nuclear charge of chlorine being the maximum, therefore it will have the lowest radii possible. Like that was my that's how you're supposed to answer it. Okay, so as the effective nuclear charge increases, as the effective nuclear charge increases, the ionic radii decreases. Okay, so in case of O2 minus, F minus, Na plus, and Mg, the nuclear charge are respectively plus 8, plus 9, plus 11, and plus 12. Thus, the order of the radii are, though, who has the maximum number of protons? Magnesium. So it will have the smallest ionic radii. Who has the least number of protons? Your oxygen. So it will have the it will have the biggest ionic radii. Understood? Okay. So we have officially finished the syllabus. What I wanted to do is go through the periodic classification once more. Okay, read the intricate details from the Arihant book. Okay, and if you have any questions, please let me know. Are there any questions? Okay, so please send me the question paper for your tomorrow's exam. Okay, I have already given the maths question paper to my students here. Okay, so are you confident? Decent? Okay, so if you have any doubts, I'll be awake for another 1 hour. Okay, if you have any doubts, please let me know. Okay, chalo. All the best, Rupat, for tomorrow's exam. Okay, I hope you really do well. Okay, chalo. Bye.